Perdón, está cogiendo algo aquí. The meeting is being recorded. Ah, okay. To say thank you for the invitation. It's a great honor to visit the Department of Physics of Universidad Técnica Federico Santa Maria. Yo voy a hablar, I will speak today about work that I have done with a collaborator in Uruguay, is Marcela Pelais. And the idea just to introduce the concept of QCD effective charge. So I will just to introduce the main ideas, the initial ideas about what is a QCD effective charge, and I will show how this concept is very useful to find a solution for a problem that is a good description of the structural function in the infrared region. Okay, so the talk I will start with just to talking a little about the structural function F2, and the problem is how to describe the structural function in log Q square and small x. So I will just to introduce why we need non-perturbative physics. We need non-perturbative correction to describe the structural function in this kinematical region. I will discuss a little about the problem, how to incorporate non-perturbative correction to F2. And I will show our solution, that is just to introduce the idea of QCD effective charges. And I will discuss the introduction of high twist contributions to F2, because in this work we have introduced QCD effective charge, and we have added high twist contribution to improve the description of structural structure. I will talk about some results and conclusion and perspective that we are doing now in this exact time. So just to remember, the data on structural function, the main source of the data is looking at deep elastic scattering. Okay, so this is the instrumental tool to obtain high precision of the data. Okay, high precision measurements of the quark and gluon contents on the nucleon. And here just a very well-known diagram about the deep elastic scattering. So we have an electron, for example, a lepton in general. So we have a photon transmitted, and this photon will achieve the proton here. So this blob here just to means our ignorance about the structure of the proton in terms of gluons and quarks. And in deep elastic scattering, we have the production of hadronic products here that have invariant mass given by x, okay, and a momentum there, k line, p and p line is for momentum transferred. Okay, so that's the experimental form to obtain data on the structural function. So structural function will be related with the distribution here in the blob about quarks and gluons. We have some kinematical variables important in the process of a deep elastic scattering, that is basically the virtuality of the photon, that is is related with the momentum transfer square. Okay, minus q square is the t, the Mandelstam variable t, and you have the variable, the x of Bjorkin, defined in this way. Okay, so we have some considerations here. For example, the high energy limit of this process is when we have this Q square larger than m squared, then m squared here can be, for example, the mass of the proton. Okay. Okay. Well, the nucleon structural function F2 at log P has been measurement in the Hera collider. So we have the Atlas and Zeus experiment that have a lot of data in this kinetical region at log Q square. So, but the question is, a long-standing question is, the extent to which the non-perturbative properties of QCD affect the behavior of F2. So the log Q square in small x regions bring us into a kinetical region where non-perturbative QCD effects become essential. I will try to show this more clearly, but anyway, the question for us, one of the important questions for us in this region is very interesting kinematical domains to test new QCD theoretical ideas. So that's we have done. Here I'm just introducing the data that we try to describe. Okay, so you see that you have done implemented a global fit of data. So in this data we have data in the experimental region. We have some pointer. If you don't have pointers, there is no problem. I will try to use my arm. And in this part, we have data in the perturbative region, and in the upside, we have data in the infrared region. That means that data, when the Q square is not is lower than more or less one GV square. Okay. So the first thing is just to see that in fact it is necessary non-perturbative corrections. Okay. So I will try just to see very quickly to show why correction arise in this kind of data. Well, we know that at sufficient and small x, the power series in this time, alpha s is the coupling here, times this kind of logarithmic, may be resummed via BFKL equation. So here I have just to talk very quickly about what I mean for resummations in QCD. Okay, the first point is every physical observable can be written in perturbative QCD as a power of a series in the coupling. Okay, we have to have some conditions to this be true, but in general this can be implemented. So what happens is when you do such as power series appears, we see the appearing of many logarithms. Okay, logarithms, and you have to resume this kind of logarithm. When I say resume, I'm saying we have to take in account this to follow with our calculation. So, but there are basically two kinds of logarithm that appears in this kind of a series. One of the kind of logarithms is like that when I have the coupling times the logarithm in terms of the Q square, in terms of the scale. Okay, the momentum transfer square, for example. This is the virtuality of the photon. You can see it this way. So to sum this kind of logarithms, you can use the Diglep equation, because the Diglep equation sums of all orders in the coupling, okay, contributions like that. So, but the Diglep does not include this kind of a singularity that is a soft kind of singularity, is another type of logarithm that is proportional to the inverse of the Bjorken scale variable. And this we have to use the BFKL equation. So in a resume, the BFKL equation describes the x evolution of the partial distribution function at fixed Q square. So if you remember, the Diglap equation described the Q square evolution of the PDFs at fixed x. Okay, so that's the symmetry that you can compare one of other. So just to be a little more precise, we have the following. We have phase space regions, okay, and dependent of the phase space region that you are working, we have one kind or more another kind of logarithm. For example, if I have, for example, the coupling, so if I work in a kinematic region, or in other words, a phase space, when I have the coupling times this kind, this LQ is the logarithm of this kind, okay, in short. Oops. Here I don't see the change in my. I'm changing here, but I'm not seeing the change in here. No, please. Yes. So when I write LQ with index Q, I'm talking about this kind of logarithm, okay? And when I talking about LX, I'm talking about this kind of logarithm, okay? In short. So when I have, for example, just a minute. Again, I don't know if I seen the same. I'm in the page 8 here. Here I don't know. I think this is page 7 or not. No, this is the. This okay. Okay, now it's okay. Sorry. So if you have, for example, you are working in a kinetical region when the coupling times this kind of logarithm is around 1. This in this same region we have the coupling times this kind of logarithm is smaller than 1, very much smaller than 1. So we have some behavior when you see each of these transversal momentum involved in the process. So, but you have, for example, this kind of behavior here, the coupling times this kind of logarithm around 1. This is much smaller than 1. So I have this kind of ordering in the x variable. So the point is this: at small x and small q square, that is the phase space when gluons are dominant. So, but we don't have strongly ordered KT, transversal momentum. So what it means? That means that you have to integrate over the full range of the transversal momentum. So what is the consequence of this? So the consequence that you will have to work with the unintegrated gluon PDF that I call G tilde here. So G without tilde is the PDF that we work usually work, okay, from the Diglap evolution equations, and G tilde is this unintegrated gluon PDF, and the relation between G tilde and G is given by this equation, for example. So the usual PDF from Diglap is related with the integration, okay, in the full range of KT square of the unintegrated gluon PDF. So that's the price that you have to pay when you're working with this type of phase space. Here I have just a diagram just to understand it better where is the KTN, KTN minus 1 and the respective behavior for the X, okay? And okay, that's one thing. The other thing, okay, if you looking for the behavior of the gluon distribution, the unintegrated gluon distribution, we know from the BFKL that the behavior can be parameterized, is done by this. This is predicted by the BFKL. Okay, we have new results today that the lambda is not exactly 0.5, but okay, even today we have a behavior very similar to this kind of behavior. Okay, so and just to
also for ray behavior.
Sorry.
Behavior.
Sorry, can you repeat this?
That can be obtained from Brady behavior.
Ah, yes, yes, exactly. And here I have the connection between another kind of the connection. It's the same that before, but now just to showing that is related with the partial derivative of this. Well, the point is, it is clear now because the contribution of non-perturbative contribution are very important. First, the resolution program requires knowledge of the gluon for all range of KT square, okay, including the deep infrared region. Second, the data in the small x region show that F2 tend to a flat shape with decreasing Q square. So you can see this again from this data. Just to show the data again, is the page 5. When you see exactly in the region, when you go to the non-perturbative region, okay, we see that in the perturbative region, you have this kind of inclination of the data, but when you go in the direction of smaller and smaller Q square, the behavior is like this decline of the inclination, okay? Anyway, this is not expected from the perturbative treatment. So it's a signal of non-perturbative contributions that you have to take in account. So the question is, if you try to, before please, here. You see that approaching to the log Q square region from QCD theory makes evident the problem of how to incorporate in an effective way non-perturbative corrections in the description of the structural function. So the problem is given. So the question is how to do that, how to achieve a good description of F2, okay? So as I said in the beginning, our approach, it was just to introduce the idea of effective charge in QCD. But before, just to be more exactly why we have what we are doing, we have just observed a very important point in our approach, that in the limit of a small x region, there are some analytical solution of the Diglett equation. Okay, so these analytical solutions are valid only in the very small value of x. Okay, so however, we know that the data at small x can be interpreted in terms of the double asymptotic scaling phenomenon. That is. It was observation of many years ago. That means that we can treat the F2 using only 2 new variables, okay, to treat all the kinematical regions that used in the experimental data, okay. So and more than this, the analytical solutions can be extended in order to include the subasymptotic part of the Q square evolution. This is a it is known also for many years ago, but the name of this is generalized DAS approximation. So since the beginning, we are working in the generalized DAS approximation. Okay, that's the first point. So our results that you show are valid only in the region where x is very, very small. Okay. Well, we have used a formalism given some time ago also by sorry, the next one. Yes. Obtained by some time ago by Leonard Kotkov and Parent, that the idea is more or less, the idea is to work with representations in Milan space, and with the Milan transform, you can find it to use to write your results in terms of functions that are functions from of x and q squared. Okay, so we are using the same representation with a small difference, but essentially is the same formalism that you have used, and this work in 2011. We have used a leading twist formulation to describe the F2. Okay, so we have seen that when you have introduced the data in the deep infrared direction, the leading twist solution was not so good. Okay, so we have seen that it's possible to introduce high twist correction. That we resume is just to say that your data, the total structure function is a combination of this leading twist. Okay, so we have obtained some time ago a solution for this, and now we have to introduce more terms that is proportional to q squared, q to 4, and so on. The name of the terms are high twist, okay, contributions.
And that expansion doesn't work at very small magnitude.
That just a minute. We see that in fact this is not true, but this is not true if you use the idea of effective charge, because this kind of problem is related basically with the behavior of the coupling in very small square, like q squared. Give me some minutes to try to convince you that with this. So just to introduce some technical difficulties, here we have Carlos Contreras and Gorazd Cizvetic that are expert in this, so they know more than this than I. But the idea is very simple, not very simple, but the idea, the question when you introduce high twist terms, we have theoretical difficulties in controlling power correction. The idea is basically the following: if you introduce the next twist term, we see that we have some ambiguities that appears, but we see that if you take the terms after the leading twist, the ambiguities can be combined with the ambiguities in leading twist, and the things work more or less very well. But the idea, if you introduce, for example, a twist 6, okay, in your expansion, we have the introduction of a lot of ambiguities again, and not necessarily these ambiguities will be compensated by the ambiguities in twist 4. So what you can do is say the following: when the ambiguity in twist 4 are cancelled by ambiguity in leading twist, we call this the phenomenological, okay, approach. We are just saying that, okay, let's suppose that the phenomenological, there is no theoretical that this is true, but it's the only way to follow ahead. Is to say that, okay, there is a mechanism very similar to the phenomenological that you can do the same thing of the cancelling between ambiguities from the twist C's with the twist 4. Okay, so this is a choice, and this is what called the phenomenological approach. Okay. Well, this is a little more technical things about this kind of ambiguities and this kind of what in fact you have to do in a formal way to treat with these ambiguities, okay? But in sum, we are using this approach called infrared anomaly model. That is to say that, okay, we are supposing that the ambiguities between twist 4 and twist 2 can be used for when introducing more terms of twists. Okay, so we have calculated the contribution of this kind of correction. So twist 4 can be written in this way. Okay, and we see that the twist 4 is a convolution of this kind of a function that appears in the leading twist with this term that have this contribution that is in twist 4, but this is well known and is obtained by means of the infrared anomaly model, the original anomaly model. Okay, so we have, for example, the contribution up to twist 4 can be written in this way. So we can write finally to find what the expressions from this next twist contribution. We have done this in 2012, and we have seen that in the same way the twist 6 can be incorporated in the same using the same idea. So now we have again a convolution between things that we know very well from the leading twist with the terms that have to be calculated in twist 6. And again, this kind of function can be obtained using the infrared anomaly model. So we have finally is able to calculate all these terms until the twist 6. Okay, so the idea is just to, okay, let's go to the next twist term and compare with the data. Okay, it worked very well or not very well? Okay, no, not very well. So let's go to the twist 6 and so on. So here I have just I'm showing the expression just to see that it's a complicated expression, but the most important here is that our expansion can be written in the analytical way, okay? But inside of the analytical expression, we have the presence of the couplings, the strong coupling here, okay? Alpha strong. Even if you use until up the twist 6, when you use here the coupling predicted by perturbative QCD, the things do not work. Okay, so we have seen that it's missing some ingredient here because if you introduce more twist terms that expected to improve your expression, unfortunately, it was not possible for us because the data that we are using are in very, very deep infrared region. Okay, so the idea is to change this kind of coupling by the QCD effective charge. And here a very fast introduction to QCD effective charge. Okay, so the first thing that you have to know that the non-perturbative dynamics of QCD may generate an effective moment-independent mass. And the name of this is dynamical mass. So today, this is a reality. If you take the people working in QCD, let's say QCD, and the people working Schwinger-Dicke equation, okay, it's very clear that we have the presence of a dynamical mass for the globe. Just to pay attention that this is not the mass that appeared in the Lagrangian of QCD, for example. This is a dynamical mass. It depends of the scale, depends of the momentum Q square, for example. And this mass goes to 0 in the regime of high Q square. Okay? So this is another thing, another type of mass, okay? It's just a momentum-dependent mass that appears naturally in the studies of QCD, lattice QCD, or in the studies of Schwinger-Dyson. Because Schwinger-Dyson equations are non-perturbative, is also a non-perturbative tool to study the QCD in the region of non-perturbative region. So, but the point is, we have many results today when people work with large volume lattice QCD simulations, both in SU2 or in SU3, and this reveal that the Bloom propagator is finite. That's the point. The Bloom propagator is finite. If you work in quotient or not quotient approximation in lattice QCD, the results of many groups shows that the Bloom propagator is not infinite, it's not divergent, okay? So, but from the point of view of Schwinger-Dyson equation, this means that a finite Bloom propagator corresponds to a massive Bloom, okay? So, corresponds to a Bloom with a dynamical mass. That's the relation between these two kind of non-perturbative tools, okay? And because this, we can introduce what you call the QCD effective charge. That's true is a non-perturbative generalization of the canonical perturbative coupling of Strong. Okay, and this QCD effective charge is related with the phenomenon of dynamical glow mass. Okay, because the QCD effective charge takes in account dynamical glow mass. Okay, so in fact, this kind of QCD effective charge provides the bridge leading from the deep ultraviolet region to the deep infrared one. Okay, we have basically two forms to obtain a QCD effective charge. Okay, but if you use one or if you use another, they have, in fact, they coincide very precisely in the deep infrared region. Okay, in the infrared region, when you're talking about Q square around 0.7 or until 1, we have a small difference between the two approaches, but infrared they goes exactly to the same behavior. Okay, and the reason of this. It was observed very recently that is due, we have also kind of identity, okay, that's a non-perturbative identity relating the green function of the theory, and because of this identity, we know that these things have to have the same behavior in the when you go to the limit Q square going to 0. Okay. Example, just to see what I'm talking. This coupling, the charge can be obtained, for example, from the Schwinger-Dyson solution of the Bloom self-energy. And the idea is that I'm just showing this because this is the kind of approach that the people in lattice QCD use. Okay, so they define in this form. In this definition, the solution for the Bloom self-energy are used to form a quantity that is invariant, a renormalization group invariant. Okay, when I say renormalization group, that does not depend of the renormalization scale. Okay, just this, and this can be written in this form. Okay, this is the most general form that I can write. Okay. The inverse of this quantity, renormalization group invariant quantity. And when you use this, you see that your charge has exactly this behavior here. This is in leading order, okay? Just as example, we see that you have to do the same procedure in next to leading order, for example. So you see that following, you see that that expression is very similar to the expression given by the perturbative QCD. Okay, the only difference, for example, from this expression from perturbative QCD, if I do this change here, okay, so it's the contrary. Okay, if I take my expression for the effective charge and I do this kind of the transformation here, we see that we obtain exactly the behavior of the leading order coupling predicted by perturbative QCD. Okay, so as I said, it was just an example because given some properties about the normalization, you see that we can do the same thing with, for example, the next leading order of coupling. So you have the equivalent to the next leading order effective charge. Okay, so the idea, and you see that a very interesting thing, that in fact you can obtain the please just one before. Thank you. You can obtain the expression for the QCD effect charge just saturating the scale. What is that? We have just to take the expression for the coupling next leading order. We have in place of this, you have a Q square, only Q square. And if you change the Q square for this form, we have exactly the expression for the effective charge next leading order. And this expression is exactly the same expression if you have that you can obtain using, for example, taking the solution of a gloom self-energy and doing all the procedure in Schwinger-Dice equation. Okay, so the question is, the gloom has a dynamical mass. This is an effect of the dynamical symmetry breaking, but what is the behavior of that mass? Okay, the behavior can be obtained again studying the Schwinger-Dice equation. Okay, and you have seen that there are basically two kinds of mass. That one kind I call logarithmic behavior, and the other is the polar law behavior, that have this distinct behavior. So there is another one that can be obtained, not just saturating, that's what I've done, but if I take the Schwinger-Dice and do all the procedure, there is a very particular combination to obtain that renormalization group invariant variable that I have shown before. And with this combination, we see that's possible to see a third one behavior for the coupling that is given by this. And this is basically, we have to introduce more ingredients here. And it's basically, we can see that the behavior, parts of this behavior can be calculated using a Lagrangian of the Cauchy-Ferrari. Anyway, the idea, so now I'm just explaining the asymptotic behavior of the coupling, okay? Since the dynamical mass goes to zero in large momentum, so the effective charge, QCD effective charge, is exactly equal to the coupling charge, to the coupling obtained from perturbative QCD, okay? So you can see that this kind of a QCD effect charge is a kind of, it belongs to a class of holomorphic couplings, that is the couplings that the people here in Chile are very competent in work. Here I have just the comparison between, this is the canonical QCD perturbative coupling, and these are the three different couplings, the logarithmic, the polar law, and the Cauchy-Ferrari. So there are three distinct behaviors that you have in the infrared region, okay? So here, just to introduce the results, so we have just to take in a lot of data from Zeus and H1 collaborations, okay? In which the function F2 is the most important. We talk this in some seconds. We have used a Q-square procedure using a confidence level of 90% and so on. And we have a fixed the number of a flavor equal to 3, the lambda equal to this value. So in the paper, you can see the reasons for that. And here I have the first results, okay, for the description of the structure function. So here we see the results only for the leading twist, only taking the leading twist plus the twist 4, and here taking the 3 terms, okay? Leading twist, twist 4, and twist 6. And we call attention that usually the scale of the dynamical mass is an input in many approaches, okay? Many papers that use this idea of dynamical gluon mass. And here, for the first time, you have not an input, but it's an output of our the scale of dynamical mass, okay? So this is the result using the logarithmic effective charge. This is the result using the power law effective charge. Again, you see that it's necessary to use all the terms because only these will have a Q-square there, okay? And close to 1. And here the result using the Cauchy-Ferrari effective charge. So here I have the description. This is for the logarithmic, I think, for the only the leading one, the leading more plus twist 4 and all is the solid. The solid curve is taking all the terms of the high twist. And you see that, in fact, you have a good distribution of all data, mainly in the infrared region. The same for this power law, and the same for the Cauchy-Ferrari coupling. So here, just the comparison between the 3. But here the results for all the terms, twist 4 plus twist 6, but comparing the 3 dynamical masses. So you see that, in fact, that is not possible to see what is the best behavior for the dynamical mass, because the 3 behaviors given a very good description of the data. And more interesting for us that with this formalism, you can extract what is the gluon parton distribution. And here we have just compared our results with the last or the more actual post-LAC gluon parton distribution. You can see that this yellow is the uncertainty, okay, in chi-square equal to 2, 10, 10 to 2, and 10 to 3, okay? And you see that our results in very small x are very compatible, okay? We have a very good description of our results are very close to the results given by these groups, okay, in determining the gluon parton distribution. Well, what are you doing now? Basically, sorry.
Can you go back to
Yes.
about this picture with the
This?
no, with the 3 tweets?
Here?
No, go back. And you the result on the
I think it's after
fitting,
that.
is fitting. Fitting. No.
The table?
The table with the fitting.
Okay. The table, so it's before.
Before when you put
This.
Yeah, we see that the results very better when you consider it from just the 4 or 6. So what is the important point is the cheese. Cheese, what is the, oh, how do you know what is better for compared with
well, the only thing that you have to
those you are
is the result of a Q-square by degree of freedom.
Yes.
So this is the only parameter that we are using to say, okay, this is a good description or not so good description.
Does mean the leading twist is not enough.
No, because leading twist is almost
Very low.
3, and you see that if you see the figure, can you please, anyone, is the dotted one. You will see that, for example, we don't have even leading twist, and in some cases, if you take only the twist fork, we have these 2 curves, only the solid. We see visually, you see that is a good description, and you see that in fact this has a smaller value of p squared by the degree of freedom. Okay. Okay.
How do you consider here?
Sorry.
How many points? Experimental data.
The total we have in the table.
Ah,
Can you please the table? We have in the total some any table. Here we have in the total. In this case, we have 250 points, experimental point, because this is the degree of freedom. So with the total, the total number of data minus the number of free parameters. So because these you have in the case divided, because you have to introduce 2 more and here 2 more. Okay, but the data, the total of data are 250 data, including all the data, the perturbative region and non-perturbative region. Okay. And what are you doing now? When you go for this, okay. As for example, we have used experimental data. No, one
Next.
more. The next 8 here. We have used only the data that we know from the experimentalists that in fact the data is basically only to F2, because we have many data when in fact what is observed in laboratory is this. Okay, this is the co-effective reduced cross section, and this is always the combination of F2 and the longitudinal structure function. Okay, so we now just to see how to calculate using this formalism. Is it possible to find some expression for the longitudinal and structure function? If yes, we can relax and use it, more quantity of data, and you have to when we have control of this, okay, and use finally the reduced cross section, okay. And this is important because the longitudinal structure function has a more direct relation exactly with the gluon distribution function. And the idea, if you have a formalism when you have to use F2 and the longitudinal, you can in some way to impose some constraints to see again what is the behavior of our gluon partner distribution function. And this open a window for to calculate many things and compare many things. Okay, so that's I would like to show. Thank you.
Well, first one, it seems to me that your approach depends on the process. So if you apply the same thing to neutrino, for example, the whole thing has to be done completely again.
Exactly. Yes. So, but this is a general. You don't have a general approach that if in general we have to change one thing or other. So to use, in fact, when you use if you are trying to describe, for example, structural function related with neutrino or something like that, we have, for example, other kind of structures that are much more important for that process than here. For example, here, using just compare with hadronic collisions, F2 is important. For example, but if I try to describe the neutrino with certain function, F3 is very important, for example. So, yes, see, yes, but I agree with you.
That's my comment. The second comment.
But the F2 that appears in the description of the neutrino, for example, is the same F2. So you can use a global, you can in fact obtain a description, a good description, including this kind of process, just mixing this kind of structure with the new data of neutrino. It's a very good idea.
But you have to see in terms of structure, distribution function. And in that case, it's the same.
Ah, yes, 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 I agree, yes.
So it's an approximation. I mean, you're separating the hard scattering from the distribution. That's an approximation. The other thing is that according to your thing, for example, the momentum sum rule has to be violated. Kind of is correct. Because the small x is not going to follow any. It's absolutely different from the other. So if you put your approach in terms of the distribution function, the integral is not going to be 1. So the momentum sum rule has to be violated. But I agree with that. I don't say that's one point. The other thing is, I tend to think about higher twist, usually in terms of the picture that we have, that I have of this, is final state interactions, but those give you the higher twist. Those are there. I mean, so you know, the thing that you're doing is missing the sort of the physical picture. I mean, it's mathematics, but what is the physical picture? Hard, you know, high twists are completely related to final state interactions. Because they give you a power, I mean, because of the change of gluons in the final state. Obviously, they give you power corrections. Those are that's just one comment there.
Yeah, no, but I agree with this comment.
I tend to
In
think
fact, I
that-
have a thinking a lot about this. I agree with you. But the point is that I think the magic word here, the magic word is renormalization.
You're
If I can
thinking
explain.
of matching the thing.
For example,
I don't see any matching.
you don't see
Like I
anything
said,
with the experimental data.
with your setup, I mean, it's completely different your setup because it's hard to follow, it's hard to see a physical picture of what you're doing.
Yes, yes. I will try
No,
okay, let's start with OPA, okay? Operation orbit expansion. In fact, if you start from OPE, you see, for example, that, well, I don't remember now the expression here, but anyway, you see, for example,
the Hamburg diagram.
okay.
That gives you the leading.
Anyway, you see that the
Because
OPA, to have an expression in OPA,
okay. And all that.
that's the reason that you have to have, for example, if you write your OPA in terms of x, not exactly this x, but x and me, that's the count, that's me is proportional to some scale square. You see that this is valid only on q squared goes to infinity. That's the initial discussion. Okay, so. But the point is, what you have to do to achieve this kind of formulation. In fact, we start for OPA, but we see that in fact, when you introduce interactions in your things, you see that in fact appears necessarily a kind of scale in your problem. And this scale, using renormalization, you can transform the q squared that goes to infinity. You have to go to infinity to OPA to be valid. We can transform this for a finite scale. That is our q squared. That's the point. And in fact, we try to see all the picture of what's happening. And the only way to do that is through renormalization. And this is true that, for example,
normalize if you have normalized. You can normalize without.
Okay, well, I'm doubting of this kind of normalization starting from OPE. For example, look, if you take the series of OPA for a theory that have no interaction, or for example, a scalar field, you have a kind of behavior. But if you introduce like a strong interaction, you see that necessarily your physics is completely different, and the terms that appear in OPA are different. So the point is,
Of course, because the twist is dimension minus spin, so you have to.
yes, exactly. But anyway, I mean, just using this to say that, because I think if I understand your question, this question can be is the same. I don't know. Maybe I could be wrong. Please correct me. But for example, you can say, for example, you see, okay, you are using Q square that is finite compared with the data, but this kind of scale that's meaning only if it goes to infinity to OPA to be valid. So what are you doing?
Well, obviously, the corrections are 1 over Q squared, and that tends to Q squared goes to infinity to be exact. But it doesn't mean that it's not a good limit. It doesn't have to be Q squared. It has to be Q squared much larger than the lambda squared, the scale of QCD. Okay. But anyway.
But okay,
Comments?
I think that I understand your point.
Well, you have to try to have more physical picture. How to get the physical picture of what's going on. That's all.
You can, for example, if I could not speak about OPA and to talk just to start with, for example, about what is the description of a structured function, just using the tools that you have from perturbative QCD. Okay, so you can write this usually. Okay, there are two ways to treat this. There are the people that work with numerical tools, and there are the people that, okay, it's easier to try to work with the Milan space, and after you do all the things in Milan space, and goes to the space with the panel of Q squared and X, for example. All these things work very well in the Milan space, because in Milan space, what is important is the anomalous dimension, okay, of the anomalous dimension. Okay, the name anomalous dimension, but it's just as the Fourier transform of the splitting functions, okay. But anyway, and the anomalous dimensions are very, very important in Schwinger-Dyson, for example. And in fact, to treat with this data in very, very small momentum, we have to have a very special behavior for the dynamical, to the anomalous dimension, for example. And this anomalous dimension, this special behavior is only possible if you introduce a scale in the mass of the Bloom. That is exactly the dynamical mass of the Bloom. So why these things works? Wow. I don't know. Anyway. But this is a kind of phenomenology. Okay, this is a kind of phenomenology. Yeah, the idea of phenomenology is with the time to reduce the number of free parameters. So maybe I can.
Yeah, but I'm concerned for something. I have so many other questions, but I don't want to take too much of the time. But I don't understand why you can have this, okay, you need with respect to the analysis, and then you go to nearby something that has to do with the analysis. So how can you apply the same here and there? It doesn't make any sense to me. I mean, it's a different process. It's a very different situation. You're talking to Schwinger-Dyson about. I don't know what you're Schwinger-Dyson probably is about the propagators or something like that, right?
Yeah. Well, this point, okay, this is important. The question is, in fact, to do this some kind of phenomenological work using this, we have first to find some process that is sensitive to this dynamical mass. We don't have many processes in many different kinematic regions that we don't see any sign of dynamical mass. So the first difficulty is just to find some process that will be sensitive to this. And this is one of the processes. I don't know if, for example, we can try to see what happens if I try to describe the structure function related with neutrinos, for example. I don't know. What is the sign of this in F3, for example? Probably, okay. There is no sign because we don't have a strong interaction here. Okay, but okay, I can find another kind of example. But the first difficulty is just to discover some process that is sensitive to this. That's why we are using, for example, this kind of a structure function. And we don't have, in fact, many processes that you can use just to test this kind of dynamical mass, the sign of dynamical mass, for example. We know, for example, we have some work that we have described the total cross-section of proton-proton scattering, for example. Okay, there is some sign. There is, but it's not necessary. That's the idea. But in this is very necessary. We are trying now to use the same idea with another completely different process. That's again the diffractive scattering. When I use a model, so well, in phenomenology we have to use models, and we have to take in account sometimes many things. Okay, fix many things. But we try to use, for example, a model that describes the interaction, the pomeron, the change of the pomeron between the protons, like two gluons. Okay, it's not a new idea. There is a Landschaft-Nachman model. There is a lot of models that describe this, the pomeron, like two gluons. But we see that this is a very interesting model to introduce the dynamical gluon mass. And you have seen, for example, because we are trying to do that, because there was a model from 20 years ago, and there is a paper from 2 years ago that the people from Belgium, I don't remember, have tried to use this model for the new data for LAC. It's not possible to describe the data, okay? And you have seen that the description is perfect, just using the idea of dynamical gluon mass.
So the dynamical gluon mass I can do. I'm not saying that that's incorrect. I mean, it's just the fact that you don't interact and you can sort of define the effective mass that depends on the neuron because it's interacting and blah, blah, blah. You prepare all like that. I mean, it's no idea.
Yeah, but the fact that you have an effective mass is not exactly the dynamical mass.
Now you are talking.
I hope to do you, man.
Yeah. But thank you.
For example, let me continue. You're talking about neutrino. If you think in terms of finer state interactions, then even if two of the neutrino is going to be exactly the same as 52 for the electron. So only if you take the quantum model.
Yes.
No, that's
Thank you.
okay. Any question?
Yeah, because one suggestion there, this squared are so low there, you could phenomenologically introduce 1 over q squared plus m squared, which is one new parameter which stabilizes the first Hartree term. Yeah, it's very low q squared. Now, maybe you don't need then 6 terms there, but just 2 of them. Depends. I mean, if this kind of phenomenological regularization of OPE, the next to reading this term, will stabilize this. Perhaps because I see that your psi square goes slowly toward 1 when you use more terms.
Yeah.
The problem is that Q squared is so low that
Exactly.
Well.
That's the point. We see that, for example, if you take the data only in the perturbative region, the leading twist is good. It's not necessary to take any idea of a charge effect, QCD effect charge. The point is just this: we have introduced data on a very deep infrared region. And this you see that the stabilization stabilize only when if you take the twist, the twist 6 contribution. So
where do you see that twist 6 is better? Twist 4 is which part of your experimental field?
sorry.
No, did you see again the result of the table? There for twist 4 or twist 6 is not too much different.
No, there's difference. If you put, for
But
example, the
Q
table,
square,
well, in fact, depends on the kind of
where
but for example,
go back to this first?
the table.
The table.
Yes.
Go. Stop it.
For example, this. We have
Yeah,
1.38 and here 1.
Yeah.
Okay,
We
you
compare
say.
with this one.
Yes, and you
This is-
see, okay, and you see, okay, there is no much difference between these. This is 1.4 and this 1.2. I agree with you, looking only for this.
Yeah.
But if you see the description, we see that in fact this improvement here is due only to description in very deep region. If you see the figures now, because okay, if I don't see the description, I can see that okay, this is okay. 1.4 is okay. 1.2, okay. But if you see the figure, can you please? And you see that in fact only this curve, that is the solid curve, in fact describes the data in very deep.
Yeah, but the solid twist for
twist 6.
The twist 6 and the
twist
other
four,
two.
where is this?
Yes.
I see.
No.
I think, where is the twist 4? Is
Okay, here no.
same position for more or less twist 6?
I think
Or
it is
not?
mixed the
Yes, indeed.
leading and twist 4 here.
You
Because-
on 5 look like.
Because you see that with they go approaching one of the other, okay, when you go here is more, we have some difference between two, but you see that they go very close one of the other. But this small difference between the data in very deep region, because the difference between the two square is not very large. But you see that description, when you see the description, we see that in fact, the inclination is only obtained if you use the twist 6. So I agree that when you see only for the Q square by degree of freedom, it's a good parameter, but it's not. We don't have to believe this all the time. It's a good parameter to see if you are going to have a good description or not. But there are new statistical tools to improve and to see if in fact your description is very good or not. Only looking at the parameters, statistical parameters. But here I have just used the Q square by degree of freedom because I have the description looking for the data, comparing the data of the theory.
Okay, I think the last question because we are trying to use this room.
Okay.
Sorry, I forgot this. Okay, thanks.
Thank you.